In the cosmic ocean that surrounds us, there exists a world that haunts our dreamser planet so tantalizingly close that we've named it humanity's next home. We tell ourselves that Proxima Centauri b, our nearest potentially habitable neighbor, is just a matter of engineering and time. That with enough innovation, enough determination, enough resources, we'll eventually make that 4.24 light-year journey. We've walked on the moon, we've sent robots to Mars, we've photographed the edge of black holes. Surely, reaching our cosmic neighbor is just the next logical step. But what if everything we believe about reaching Proxima b is wrong? What if the universe itself has constructed an impenetrable wall between us and our stellar neighbor, a barrier so fundamental that no amount of human ingenuity can overcome it? Join me as we explore the crushing reality of why humanity may be forever trapped in our solar system, prisoners of physics itself. Before we embark on this sobering journey through space and time, I'd love to know what corner of our pale blue dot are you watching from, and what time is it in your world right now? Drop your location and local time in the comments below. August 24th, 2016. The European Southern Observatory makes an announcement that sends shockwaves through the scientific community and captures headlines across the globe. They found a potentially Earth-like planet orbiting in the habitable zone of Proxima Centauri, our nearest stellar neighbor. The planet is designated Proxima Centauri b, but the media quickly dubs it humanity's next home. The discovery seems almost too perfect. Here's a world that might harbor liquid water, might have temperatures suitable for life as we know it, orbiting the closest star to our sun. At just 4.24 light-years away, it's practically in our cosmic backyard. Scientists, journalists, and dreamers begin sketching out missions. Popular articles breathlessly describe how this could be humanity's first interstellar destination, our species' first step toward becoming a multi-star civilization. The excitement is intoxicating. Stephen Hawking endorses the Breakthrough Starshot project, aimed at sending tiny probes to Proxima b within this century. Suddenly, what seemed like science fiction becomes serious scientific discussion. The European Space Agency begins preliminary studies. NASA scientists appear on talk shows. The dream of reaching another star system transitions from fantasy to seemingly achievable goal. But this euphoria rests on a dangerous assumption that proximity in cosmic terms translates to accessibility in human terms. We make this mistake because our earthbound brains struggle with the true scale of interstellar space. When astronomers say Proxima Centauri is our nearest neighbor, we hear nearby. When they describe 4.24 light-years as close, we imagine something within reach. This cognitive error isn't accidental. It's built into our evolutionary psychology. Our ancestors needed to judge distances across savannas and valleys, not across the cosmic void. A million years of evolution has equipped us to think in terms of days of walking, not millennia of traveling. So when we hear that Proxima b is our closest, potentially habitable neighbor, our pattern-seeking brains immediately begin plotting the journey. The scientific community, caught up in the excitement of discovery, often contributes to this misconception. Research papers discuss missions to Proxima Centauri and interstellar travel timescales, as if these are engineering problems rather than fundamental impossibilities. Conferences are held. Budgets are proposed. The machinery of human optimism begins turning, grinding out plans and proposals for reaching our newly discovered neighbor. What makes this particularly tragic is that Proxima Centauri b might actually be habitable. Follow-up observations suggest it receives the right amount of energy from its red dwarf star to maintain liquid water on its surface. It's roughly Earth-sized, sitting in that Goldilocks zone where temperatures might be just right. In the grand census of potentially habitable worlds, Proxima b checks many of the right boxes. This possibility of habitability amplifies our sense of cosmic destiny. Here's a world that might harbor life, that might even be suitable for human habitation, sitting right next door in cosmic terms. It feels like the universe is offering us a gift, a backup plan, a cosmic insurance policy against terrestrial catastrophe. The narrative writes itself. Humanity discovers its future home just as we're beginning to outgrow our birth planet. Let's put Proxima Centauri's closeness into perspective, with an analogy that reveals the true scale we're dealing with. Imagine Earth as a grain of sand on a beach in California. On this scale, The sun would be a marble about 26 feet away, already a distance that would make you squint to see clearly. Mars, our current target for human exploration, would be another grain of sand roughly 40 feet from our starting point. This is the farthest humans have seriously planned to travel, and even reaching Mars represents one of the greatest challenges our species has ever attempted. Now, where would Proxima Centauri be in this sand-grain solar system? It would be another marble sitting on a beach in Japan. Not just anywhere in Japan specifically, on the opposite side of the Pacific Ocean, roughly 60 miles away from our California starting point. This isn't just far, this is incomprehensibly, impossibly far. But even this analogy fails to capture the true hopelessness of interstellar travel, because it only deals with distance. It doesn't account for the fact that unlike traveling across Earth's surface, there are no rest stops in interstellar space, no gas stations, no opportunity to resupply, repair, or reconsider. The journey to Proxima Centauri b would require traveling across 25 trillion miles of absolute vacuum while carrying everything needed for the voyage. The numbers become even more staggering when we consider travel time with our current technology. NASA's New Horizons spacecraft, one of the fastest objects ever launched by humans, reached speeds of about 36 miles per hour relative to the Sun. This seems impressively fast until you calculate how long it would take to reach Proxima Centauri at this speed, approximately 78 years. To put this in historical context, 78 years ago, modern humans had barely begun migrating out of Africa. The entire recorded history of human civilization from the first cities in Mesopotamia to the present day spans only about 60 years. A journey to Proxima Centauri would require more than 13 times the entire span of human history. This temporal scale reveals why interstellar travel isn't just an engineering challenge, it's a fundamental impossibility for human civilization as we understand it. Technologies change, governments rise and fall, languages evolve beyond recognition, entire species go extinct, but a journey to Proxima b would need to survive longer than human civilization has existed. In 1905, a young patent clerk named Albert Einstein published a paper that would forever change our understanding of space, time, and the possibility of interstellar travel. His special theory of relativity introduced a cosmic speed limit that no material object can exceed, the speed of light, approximately 2 miles per second. This isn't just a practical limitation, like the sound barrier that we eventually learned to break. Einstein's speed limit is woven into the fundamental fabric of reality itself. It's not a barrier we can engineer our way around. It's an absolute law that governs how space and time interact throughout the universe. At first glance, the speed of light seems blazingly fast. Light can circle the Earth's equator more than 7 times in a single second. It can travel from Earth to the Moon in just 1.3 seconds. Within our solar system, light speed seems almost instantaneous. But when we scale up to interstellar distances, even light itself becomes painfully slow. Even if we could somehow build a spacecraft that travels at the speed of light, which, as we'll see, is impossible, it would still take 4.24 years to reach Proxima Centauri b. That's 4.24 years of perfect, uninterrupted light speed travel, just to reach our nearest stellar neighbor. No slowing down, no stopping, no course corrections. Just 4.24 years of traveling at the fastest speed allowed by physics. But here's where Einstein's revelation becomes truly devastating for interstellar travel. The speed of light isn't just the maximum speed possible, it's actually impossible for any object with mass to achieve. As any material object approaches light speed, something extraordinary and prohibitive happens. The faster an object moves, the more massive it becomes from the perspective of outside observers. This isn't just a theoretical curiosity. It's a measurable phenomenon that particle accelerators deal with every day. Electrons whizzing around the Large Hadron Collider become thousands of times more massive than when they're at rest. As a spacecraft approaches light speed, its mass would increase exponentially, eventually approaching infinity. This mass increase creates an impossible situation. The more massive an object becomes, the more energy is required to accelerate it further. As the spacecraft's mass approaches infinity, the energy required to push it even slightly faster also approaches infinity. Not just a lot of energy, infinite energy. more energy than exists in the entire observable universe. It's as if the universe has constructed the ultimate cosmic speed trap. You can go faster and faster, but the closer you get to light speed, the more the universe itself fights back, demanding ever more impossible amounts of energy, for ever smaller increases in velocity. This isn't a temporary technological limitation. We can't hope to overcome this with better engines or more advanced materials. Einstein's speed limit is absolute, unchanging, and universal. It applied 4 billion years ago when life first emerged on Earth. It applies today, and it will apply 4 billion years from now when our sun begins to die. Even more crushing is the realization that light speed already impossible to achieve still wouldn't be fast enough for practical interstellar travel. A round trip to Proxima Centauri b would take nearly a decade, even at light speed. Any message sent back to Earth would take another 4.24 years to arrive. Mission Control would be receiving 8.5-year-old information about a spacecraft they could no longer meaningfully control. The speed of light limit means that even in the most optimistic scenario that violates known physics, interstellar travel remains barely feasible. And we haven't even begun to address the engineering challenges, energy requirements, or human factors that make such journeys impossible in practice. Einstein's special relativity didn't just change our understanding of space and time. It erected an impenetrable barrier around our solar system, a cosmic quarantine that may keep humanity forever bound to our stellar neighborhood. The speed of light isn't just a limit on how fast we can go, it's a limit on how far we can ever meaningfully reach into the cosmos. Einstein's special relativity doesn't just place a speed limit on interstellar travel, it creates a cascade of physics problems that become more insurmountable the closer we get to achieving anything resembling practical interstellar speeds. These aren't engineering challenges that clever design might overcome. They're fundamental features of reality that make interstellar travel exponentially more impossible as we try harder to achieve it. Let's start with time dilation, perhaps the strangest consequence of high-speed travel. As a spacecraft accelerates towards significant fractions of light speed, time itself begins to slow down relative to the rest of the universe. This isn't science fiction, it's measurable reality. GPS satellites must account for relativistic time dilation to maintain accuracy, and particle accelerators observe it constantly. For interstellar travel, time dilation initially seems like a benefit. If you could accelerate to 90% of light speed, the journey to Proxima Centauri b would take only about 2 years from the perspective of travelers aboard the spacecraft. The 4.24 light-year journey would feel much shorter to those making it. This apparent advantage has led many science fiction writers and optimistic futurists to suggest that time dilation makes interstellar travel feasible. But this apparent solution creates profound problems that make it worse than useless. While 2 years pass for the travelers, nearly 5 years elapse on Earth. The astronauts return to a world that has aged almost twice as much as they have. For longer journeys to more distant stars, this disconnect becomes catastrophic. A journey to a star 50 light-years away at 99% light speed would age the travelers by about 7 years, while Earth ages by over 100 years. They would return to a civilization that has moved beyond recognition, making their entire mission historically irrelevant. More devastating still is the energy problem that emerges as speeds increase. The energy required to accelerate an object doesn't increase linearly with velocity, it increases exponentially as you approach light speed. To accelerate even a small spacecraft to 90% of light speed requires energy equivalent to the total output of several nuclear power plants running for years. But mass increases make this energy problem catastrophic. As a spacecraft accelerates, its relativistic mass increases according to the Lorentz factor. At 90% light speed, the spacecraft becomes 2.3 times more massive than when at rest. At 99% light speed, it becomes 7 times more massive. At 99.9% light speed, it becomes 22 times more massive. This mass increase isn't just theoretical, it requires real energy to accelerate, energy that increases exponentially with velocity. Here's where the mathematics become truly hopeless. Let's consider accelerating a modest 100-ton spacecraft to just 10% of light speed, still far too slow for practical interstellar travel. Using the relativistic kinetic energy equation, this requires approximately 4.5 Cheros 10, 17 joules of energy. That's roughly equivalent to the total electrical energy consumption of the United States for an entire month, just to accelerate a single small spacecraft to 1/10 light speed. Now consider that 10% light speed would still require 42 years to reach Proxima Centauri b. To make the journey in a reasonable human timeframe, say, 10 years, we'd need to reach 42% light speed. At this velocity, the energy requirements become truly astronomical, approximately 8.6 chems 10, 18 joules, equivalent to the total energy consumption of human civilization for several years, just for acceleration. But we've only calculated the energy needed to accelerate the spacecraft. We also need energy to decelerate upon arrival, doubling our requirements. We need energy to power life support systems throughout the journey. We need energy to power communications equipment, navigation systems, and scientific instruments. Each additional system multiplies our impossible energy requirements. The cruel irony is that the faster we try to go, the more impossible the journey becomes. The relativity equations ensure that every attempt to make interstellar travel practical instead makes it exponentially more impractical. It's as if the universe has designed a perfect trap. The harder we try to escape our solar system, the more firmly physics locks us in place. Perhaps most crushing of all is the realization that these aren't temporary technological limitations. We can't hope that future discoveries will overcome relativistic mass increase or time dilation. These are fundamental properties of space-time itself. Einstein's equations describe not just how things work in our current understanding, but how they must work in any universe where cause precedes effect, and information has a finite transmission speed. The relationship between energy and velocity in special relativity creates a mathematical wall that no amount of technological advancement can breach. Each factor of 2 increase in velocity requires exponentially more energy, until we reach a point where accelerating a spacecraft requires more energy than exists in the observable universe. This isn't pessimism, it's mathematical certainty. The equations don't care about human ambition or technological optimism. They simply describe the fundamental structure of reality, a structure that appears designed to keep civilizations forever bound to their home star systems. Every attempt to engineer around these limitations only reveals new impossibilities, new barriers that make interstellar travel even more hopeless than it initially appeared. The theoretical impossibilities of relativistic travel become even more stark when we examine our current technological capabilities and the overwhelming gap between what we can achieve and what we'd need for interstellar travel. NASA's New Horizons spacecraft, launched in 2006 to study Pluto, represents one of humanity's fastest achievements in space travel. After receiving a gravitational assist from Jupiter, it reached velocities of approximately 36.0 miles per hour relative to the Sun. This seems impressively fast until we calculate what it represents as a fraction of light speed. Light travels at 670, 616, 629 miles per hour. New Horizons' top speed represents just 0.0054% of light speed. To put this in perspective, if light speed were a 100-yard football field, New Horizons would have traveled about 2 inches. After more than half a century of space exploration, our fastest spacecraft crawls across the cosmos at a pace that makes interstellar travel seem not just impossible, but almost comically hopeless. At New Horizons' record-breaking speed, reaching Proxima Centauri b would require approximately 78.0 years longer than modern humans have existed as a species. This isn't a minor engineering challenge requiring incremental improvements. It's a gap so vast that bridging it would require fundamentally different physics. But New Horizons represents travel within our solar system, where we can use gravitational assists and don't need to carry fuel for the entire journey. For actual interstellar travel, we'd need sustained propulsion across vast distances, making our current chemical rockets embarrassingly inadequate. The space shuttle's main engines, among the most powerful chemical rockets ever built, could theoretically accelerate a payload to about 17.0 miles per hour if they could run continuously. But chemical rockets carry their own oxidizer, making them incredibly inefficient for long journeys. The majority of a chemical rocket's mass is fuel, and that fuel needs more fuel to accelerate it, creating a cascade of inefficiency that makes interstellar missions impossible. Even our most advanced ion drives, which use electric fields to accelerate charged particles, can only achieve modest speeds over long periods. The Dawn spacecraft, powered by ion propulsion, reached maximum speeds of about 25.0 miles per hour after years of continuous operation. While more efficient than chemical rockets, ion drives still fall pathetically short of interstellar requirements. Nuclear pulse propulsion, proposed in projects like Orion and Daedalus, represents our most optimistic chemical-era thinking about interstellar travel. These designs envision spacecraft propelled by thousands of nuclear explosions, potentially reaching 3–4% of light speed. Even these ambitious proposals, which remain far beyond our current engineering capabilities, would require over a century to reach Proxima Centauri b. The Project Daedalus study, conducted by the British Interplanetary Society in the 1970s, represents perhaps the most serious attempt to design an interstellar spacecraft using known physics. Their fusion-powered probe would have required 50 years to travel to Barnard's star, needed a fuel supply equivalent to several times the mass of Mount Everest, and could only carry a tiny payload for a brief fly-by-no landing, no detailed exploration, just a few photographs transmitted across interstellar space. Even Daedalus, optimistic to the point of fantasy, acknowledged that interstellar travel represents a challenge beyond current human capabilities. And Daedalus was designed in an era of nuclear optimism, before we fully understood the engineering nightmares of sustained fusion propulsion or the radiation environment of interstellar space. Today's most advanced propulsion concepts, fusion ramjets, antimatter engines, even purely theoretical constructs like warp drives, remain firmly in the realm of speculation. Meanwhile, our actual spacecraft continue to crawl across the solar system at speeds that make interstellar travel a multi-generational impossibility. The speed gap between our capabilities and our ambitions isn't shrinking. Despite decades of advancement in materials, science, computer technology, and engineering, our fastest spacecraft aren't dramatically faster than those of the 1970s. The fundamental constraints of chemistry and physics continue to limit our reach, keeping us forever bound to our tiny corner of the galaxy. Every rocket that has ever launched from Earth operates on a principle discovered by Konstantin Tsiolkovsky in 1903, the rocket equation. This deceptively simple mathematical relationship describes the fundamental challenge of space travel and reveals why interstellar missions face an impossible energy paradox that no amount of engineering cleverness can solve. The rocket equation states that a spacecraft's final velocity depends on the exhaust velocity of its propulsion system and the ratio between its initial mass, with fuel, and final mass, without fuel. To go faster or farther, you need more fuel, but fuel has mass, and that mass needs more fuel to accelerate it. This creates a cascade effect where the fuel requirements for high-speed missions increase exponentially, eventually reaching impossible levels. For interstellar travel, this fuel paradox becomes catastrophic. Let's work through a practical example using the most efficient chemical propulsion system ever built, the Space Shuttle main engine, with an exhaust velocity of about 4.4 kilometers per second. To accelerate even a small 0 kilogram spacecraft to just 1% of light speed, still far too slow for practical interstellar travel, would require a fuel mass of approximately 390 kilograms. This number is so large it defies comprehension. To put it in perspective, the observable universe contains roughly 53 kilograms of matter. Our fuel requirements exceed the mass of the universe by a factor greater than the number of atoms in existence. This isn't a slight engineering challenge. This is mathematical proof that chemical propulsion cannot achieve interstellar travel speeds, even at velocities far below what would be practical for reaching Proxima Centauri b in human lifetimes. Nuclear propulsion improves the situation, but not nearly enough. Fusion rockets, if we could build them, might achieve exhaust velocities of 3/10% of light speed. Even with this dramatic improvement, accelerating a modest spacecraft to 10% light speed would require fuel masses millions of times greater than the spacecraft itself. The entire mission would become a fuel tanker with a tiny payload, and we still haven't solved the problem of where all this fuel would come from or how we'd store it. The fuel paradox gets worse when we consider that interstellar spacecraft need to decelerate upon arrival. Unlike missions within our solar system, where we can use atmospheric braking or gravitational assists, interstellar spacecraft must carry enough fuel for the entire round trip. This doubles our already impossible fuel requirements. But the real killer is the time factor. Chemical reactions and even nuclear fusion release energy slowly compared to the requirements of interstellar travel. To achieve meaningful acceleration, we'd need to burn fuel at rates that generate enormous power that must be contained, controlled, and directed through engines that don't exist and may be physically impossible to build. Consider the power requirements for accelerating our 10 kilogram spacecraft to 10% light speed over a reasonable time frame, say 1 year of acceleration. This requires sustained power output of approximately 4.5 chems 15 watts. For comparison, the total electrical generating capacity of the entire Earth is about 5 chems 12 watts. Our single small interstellar spacecraft would require nearly 10 times more power than all of human civilization currently generates. The energy density problem compounds these impossibilities. Chemical fuels store about 1050 megajoules per kilogram. Nuclear fuels can theoretically store much more fusion of hydrogen releases, about 630 billion joules per kilogram. But even perfect fusion, with 100% energy conversion, efficiency and magical storage systems, falls short of interstellar requirements by orders of magnitude. Antimatter represents the theoretical maximum energy density, possible the complete conversion of matter to energy, according to E max quadrad. Even with antimatter, the fuel requirements for interstellar travel remain staggering. Accelerating our 10 kilogram spacecraft to 10% light speed would require approximately 25 kilograms of antimatter fuel, assuming perfect efficiency and no fuel needed for deceleration. 25 kilograms might not sound like much, until you realize that humanity has produced less than 20 nanograms of antimatter in all of history, at a cost of roughly 25 billion per gram. Producing enough antimatter for a single interstellar mission would require energy equivalent to the total output of human civilization for millions of years, assuming we could solve the currently impossible problems of antimatter production, storage, and containment. The fuel paradox reveals why interstellar travel isn't just difficult, it's impossible within the known laws of physics and thermodynamics. Each proposed solution only reveals deeper impossibilities. More efficient engines require more advanced materials that don't exist. Higher energy densities require fuel sources we can't produce. Faster acceleration requires power systems beyond our planetary capabilities. Even if we could somehow solve every other challenge of interstellar travel, the radiation, the time scales, the engineering complexity, the fuel paradox alone would keep us forever bound to our solar system. The universe appears to have constructed a perfect energy trap, one that allows local space travel within star systems, while making travel between stars exponentially impossible. This isn't pessimism or lack of imagination. It's the mathematical reality of energy, momentum, and the fundamental constraints that govern motion through space. The rocket equation doesn't care about human ambition or technological optimism. It simply describes the physical requirements for acceleration, requirements that scale impossibly with the distances and speeds required for interstellar travel. To truly grasp the impossibility of interstellar travel, we need to confront the raw numbers, the actual energy requirements compared to humanity's total energy resources. The calculations are so staggering that they seem designed to crush any remaining optimism about reaching Proxima Centauri b. Let's start with a conservative scenario, sending a small robotic probe, weighing just 10 kilograms, about the size of a large car, to Proxima Centauri b, at 10% of light speed. This would be far too slow for human travel. The journey would take 42 years, but it represents the absolute minimum for any meaningful interstellar mission. Using relativistic kinetic energy equations, accelerating this modest probe to 10% light speed requires approximately 4.5 chens 17 joules of energy. This number is difficult to visualize, so let's put it in terms of human energy production. The total global energy consumption of human civilization is approximately 5.8 chens 20 joules per year. This includes everything: electricity generation, transportation, heating, industrial processes, and all other energy uses across the entire planet. Our single small interstellar probe would require about 78% of humanity's total annual energy production just for acceleration. But this calculation assumes perfect efficiency, that 100% of energy input translates directly to spacecraft kinetic energy. In reality, even the most efficient propulsion systems lose enormous amounts of energy to heat, radiation, and other inefficiencies. Chemical rockets achieve roughly 35% efficiency. Ion drives might reach 90% efficiency under ideal conditions. Even with perfect fusion propulsion and magical 90% efficiency, our energy requirements increase to roughly 5×10^17 joules, almost exactly equal to all human energy consumption for an entire year. Remember, we still need energy to decelerate the probe when it reaches Proxima Centauri b, essentially doubling our requirements. We also need energy for life support systems, communications, scientific instruments, and course corrections throughout the 42-year journey. Suddenly, our modest probe mission requires several times the total energy output of human civilization for multiple years. These numbers become even more devastating when we consider manned missions. A spacecraft capable of supporting human life would need to be much larger, probably at least 10 kilograms to provide minimal life support, radiation shielding, and supplies for a crew during the multi-decade journey. The energy requirements scale with mass, so our manned mission would require roughly 10 times more energy than the robotic probe. Now we're looking at energy requirements equivalent to the total output of human civilization for decades, just to send a few people on a one-way trip to Proxima Centauri b. The return journey would require an equivalent energy investment, assuming we could somehow establish fuel production facilities in the Proxima Centauri system. But let's be even more optimistic and imagine we develop perfect antimatter propulsion with 100% energy conversion efficiency. Antimatter represents the theoretical maximum energy density possible, the complete conversion of matter to energy, according to Einstein's E-max². Even with this magical technology, the numbers remain impossible. Producing just 1 kilogram of antimatter would require approximately 9×10^16 joules of energy, roughly 15% of humanity's total annual energy production. Our small interstellar probe would need about 25 kilograms of antimatter fuel, requiring energy equivalent to nearly 4 years of total human civilization output just to produce the fuel. The global electricity production capacity of Earth is approximately 2.8×10^13 watts. If we dedicated every power plant on the planet exclusively to antimatter production, assuming perfect efficiency, it would take roughly 100 years to produce enough fuel for a single small interstellar probe. During this century of dedicated antimatter production, human civilization would need to find alternative energy sources for everything else: lighting, heating, transportation, industry, and technology. These calculations reveal why interstellar travel isn't just currently impossible, it's fundamentally incompatible with planetary-scale civilizations like ours. The energy requirements exceed what any Earth-based civilization could reasonably produce, even with perfect technology and complete dedication of planetary resources. Even Type 1 civilizations on the Kardashev scale, those that have harnessed all the energy available on their home planet, would find interstellar travel challenging. Type 2 civilizations, which harness the entire energy output of their star, might make interstellar travel marginally feasible, but such civilizations remain purely theoretical and would require technologies so advanced they're essentially magical. The energy barrier to interstellar travel may explain why we haven't detected evidence of other technological civilizations in our galaxy. If the energy requirements for interstellar travel exceed what planetary civilizations can produce, then every intelligent species in the galaxy might be trapped in their home star systems, just as we appear to be trapped in ours. The universe seems to have constructed perfect energy barriers around star systems, allowing the evolution of complex civilizations while preventing them from spreading across the galaxy. We're not just prisoners of distance and time, we're prisoners of energy itself. Space, we often say, is empty, a vast vacuum between the stars. But this apparent emptiness conceals one of the most lethal environments in the universe, an invisible ocean of radiation that would slowly cook any human crew attempting the journey to Proxima Centauri b. The interstellar medium isn't empty space. It's a shooting gallery of high-energy particles, that makes interstellar travel not just difficult, but biologically impossible for unprotected humans. Galactic cosmic radiation permeates all of interstellar space, consisting primarily of protons and atomic nuclei, accelerated to enormous energies by supernovae, neutron stars, and other violent cosmic events. These particles travel at significant fractions of light speed, carrying energies millions of times greater than anything we encounter on Earth. They're the universe's ultimate bullets, and they never stop firing. Within our solar system, Earth's magnetic field and atmosphere provide extraordinary protection from cosmic radiation. The magnetosphere deflects most charged particles around our planet, while our atmosphere absorbs whatever gets through. Mars missions already pose serious radiation challenges because spacecraft spend months in interplanetary space without this protection. But interstellar space represents an entirely different level of radiation exposure. During a journey to Proxima Centauri b, even at optimistic 10% light speed, crew members would be exposed to cosmic radiation for over 40 years. The cumulative dose would be approximately 400–600 sieverts level of exposure, guaranteed to cause multiple cancers, severe radiation sickness, and death. For perspective, a dose of just 5 sieverts has a 50% chance of being fatal within months. Our interstellar travelers would receive 100 times this lethal dose. But cosmic radiation isn't the only concern. As spacecraft approach significant fractions of light speed, even tiny particles in interstellar space become deadly projectiles. Interstellar space contains roughly 1 atom per cubic centimeter, mostly hydrogen, with traces of heavier elements. At rest, these particles are harmless. But when your spacecraft is traveling at 10% of light speed, each hydrogen atom becomes a high-energy bullet. The kinetic energy of these collisions scales with the square of velocity. A hydrogen atom hitting a spacecraft traveling at 30 kilometers per second, 10% light speed, carries energy equivalent to a fast-moving bullet. At higher speeds, individual atoms become powerful enough to damage spacecraft systems and pose serious threats to crew survival. This creates what physicists call the interstellar ramjet problem. As spacecraft speed increases, the interstellar medium becomes increasingly dangerous. The faster we try to go, the more lethal the journey becomes. It's another cruel trap built into the physics of interstellar travel. Shielding provides no easy solution. Effective radiation shielding requires mass lots of it. Lead shielding thick enough to significantly reduce cosmic radiation exposure would add thousands of tons to spacecraft mass. But remember our earlier calculations about fuel requirements. Every additional kilogram of spacecraft mass exponentially increases the energy needed for interstellar travel. Magnetic shielding, often proposed as a lighter alternative, faces insurmountable power requirements. Creating a magnetic field strong enough to deflect high-energy cosmic rays over spacecraft-sized areas would require power systems comparable to terrestrial power plants. The energy needed to maintain such shielding throughout a multi-decade interstellar journey adds yet another impossible requirement to our already impossible mission. Even more problematic, some cosmic ray particles are so energetic that no practical amount of shielding can stop them. Ultra-high-energy cosmic rays carry energies equivalent to well-thrown baseballs, compressed into subatomic particles. When these particles strike spacecraft or human tissue, they create cascades of secondary radiation that can be more damaging than the original particle. The radiation environment also poses serious challenges for spacecraft systems. Electronics designed to operate for decades in interstellar space must survive constant bombardment by high-energy particles that can flip bits in computer memory, damage solar panels, and degrade materials over time. The longer the journey, the more certain it becomes that critical systems will fail due to accumulated radiation damage. Recent studies of Mars mission proposals have revealed that radiation exposure during the 6-month journey to Mars already approaches acceptable lifetime limits for astronauts. A journey to Proxima Centauri b would expose crews to radiation levels hundreds of times greater than Mars missions, making biological survival impossible. Without shielding so massive, it makes the mission energetically unfeasible. This radiation barrier operates independently of all the other impossibilities we've discussed. Even if we could somehow solve the energy requirements, the fuel paradox, and the engineering challenges, The radiation environment of interstellar space would still make manned missions to Proxima Centauri b impossible. The invisible killer between the stars doesn't care about human ambition or technological advancement. It simply makes interstellar space uninhabitable for biological life. The universe has constructed multiple independent barriers to interstellar travel. The radiation environment is just one of them, but it's sufficient by itself to keep humanity forever bound to our solar system's protective magnetic embrace. Even if we could somehow solve the impossible challenge of surviving the radiation gauntlet of interstellar space, an even more deadly threat awaits us at our destination. Proxima Centauri, the red dwarf star that Proxima b calls home, is one of the most violently unstable stars in our cosmic neighborhood, regularly unleashing stellar flares that would make Earth's surface uninhabitable and could destroy any spacecraft attempting to approach the system. Red dwarf stars like Proxima Centauri are fundamentally different from our Sun. While our Sun produces energy through steady, controlled nuclear fusion in its core, red dwarf stars are chaotic, magnetically active, and prone to violent outbursts. Proxima Centauri is particularly notorious for its stellar flares, massive explosions that release more energy in minutes than our entire planet receives from the Sun in a year. In 2016, just months after Proxima b's discovery, astronomers observed one of these monster flares using the Hubble Space Telescope. The flare increased Proxima Centauri's brightness by 68% in just 10 seconds, releasing energy equivalent to 32 joules, roughly equal to 100 billion nuclear weapons detonating simultaneously. This wasn't an unusual event. It was typical behavior for this violent star. Follow-up observations revealed that Proxima Centauri produces significant flares almost daily, with major flares occurring several times per year. Some of these flares are so powerful, they can be detected from Earth using ground-based telescopes, despite the star's distance of 4.24 light-years. For any planet in Proxima Centauri's habitable zone, including Proxima b, these flares represent an ongoing catastrophe. Each major flare bathes the planet in deadly X-ray and ultraviolet radiation, levels that would instantly kill any unprotected life on the surface. The radiation is so intense, it could strip away planetary atmospheres over geological time, making long-term habitability impossible. But the flares pose an even more immediate threat to any spacecraft attempting to approach the Proxima Centauri system. Unlike Earth's atmosphere, which absorbs most harmful radiation, spacecraft offer minimal protection from stellar flares. A single major flare could deliver lethal radiation doses to crew members, destroy sensitive electronics, and cripple life support systems. The unpredictability of these flares makes mission planning impossible. Unlike solar flares, which sometimes provide hours or days of warning, Proxima Centauri's flares can occur with no advance notice. A spacecraft might arrive in the system during a period of relative calm, only to be destroyed by a flare that erupts without warning. Even more problematic, Proxima b orbits extremely close to its star, much closer than Mercury orbits our Sun. This close orbit is necessary for the planet to receive enough energy for liquid water, but it also places the planet directly in the path of the star's most violent outbursts. Any spacecraft attempting to orbit or land on Proxima b would be operating in the most dangerous radiation environment in the local galaxy. The magnetic field situation makes everything worse. While Earth's strong magnetic field deflects much of the harmful radiation from solar flares, Proxima b likely has a much weaker magnetic field due to its close orbit and tidal locking. The same gravitational forces that keep one side of the planet always facing its star also likely prevent the planet from rotating fast enough to generate a strong protective magnetic field. Recent computer models suggest that planets in Proxima b's situation lose their atmospheres within millions of years, stripped away by the constant barrage of stellar radiation. If these models are correct, Proxima b isn't a potential new home for humanity, it's an airless, irradiated wasteland more hostile than the surface of Mars. The cruel irony is that red dwarf stars like Proxima Centauri are the most common type of star in our galaxy, making up about 75% of all stars. If stellar flares make planets around red dwarf stars uninhabitable, then the vast majority of potentially habitable worlds in the galaxy are actually death traps. Proxima Centauri's violent nature adds another layer of impossibility to interstellar travel. Even if we could somehow overcome every other barrier, energy, radiation, time, engineering, we'd still be attempting to reach a destination that might kill us upon arrival. The engineering challenges of interstellar travel extend far beyond propulsion and energy. Any spacecraft attempting to reach Proxima Centauri b must function perfectly for longer than human civilization has existed, operating in the most hostile environment imaginable, without any possibility of maintenance, repair, or replacement. This requirement alone makes interstellar travel impossible with any conceivable technology. Consider the longest operating human machines currently in existence, the Voyager spacecraft, launched in 1977, represent our best example of long-duration space engineering. After more than 45 years in space, both Voyager probes are beginning to fail. Instruments are shutting down, power systems are degrading, communication becomes more difficult each year. By conservative estimates, both spacecraft will be completely dead within the next decade. 45 years represents an extraordinarily successful mission duration far longer than originally planned. But a journey to Proxima Centauri b would require systems that operate for thousands of years, not decades. Even at optimistic 10% light speed, the journey would take over 400 years. More realistic scenarios, using technology that might actually be buildable, would require millennia. The materials science challenges are insurmountable. Every known material degrades over time, especially in the extreme environment of space. Metals suffer fatigue from thermal cycling as spacecraft move between shadow and sunlight. Plastics become brittle under constant cosmic ray bombardment. Electronics degrade as radiation displaces atoms in semiconductor crystals. Lubricants freeze, evaporate, or decompose. Seals fail. Connections corrode. On Earth, we solve these problems through maintenance. We replace worn parts, apply fresh lubricant, repair damaged systems, but interstellar spacecraft must be completely autonomous. They must carry within themselves every spare part they might ever need, every tool required for self-repair, every component necessary for system restoration. The spacecraft must essentially be a complete industrial civilization, compressed into a vessel small enough to accelerate to interstellar speeds. The redundancy requirements become absurd. Critical systems must have backups. The backups need backups. Failure in any essential system means mission failure, so engineers must plan for every conceivable breakdown. A conservative design might require 5 to 10 redundant systems for every critical component. But redundancy adds mass, and mass makes acceleration impossible. Computer systems face particularly severe challenges. Modern electronics rely on components with features measured in nanometer scales, where individual cosmic ray hits can cause permanent damage. A single high-energy particle can flip bits in memory, corrupt software, or destroy microprocessors. Over centuries of exposure to cosmic radiation, computer failures become inevitable. Even if we could build radiation-hardened computers that survive the journey, software presents equally impossible challenges. Modern software contains millions of lines of code, with subtle bugs that emerge only after extended operation. Mission-critical spacecraft software must run flawlessly for centuries without updates, patches, or human intervention. Every possible scenario must be anticipated and programmed in advance. The thermal management problem compounds every other engineering challenge. In interstellar space, far from any star, temperatures approach absolute zero. But spacecraft generate heat through electronics, life support systems, and radioactive decay of power sources. This heat must be carefully managed to prevent both freezing and overheating of critical components. Radioisotope thermoelectric generators, RTGs, the power source for long-duration space missions, present their own impossibilities. RTGs lose power continuously as their radioactive fuel decays. The plutonium-238 used in current RTGs has a half-life of 87.7 years, meaning power output drops to half the original level after less than a century. For millennial journeys, power systems must either carry enormous fuel supplies or develop self-sustaining energy sources that don't exist. Solar panels become useless in interstellar space, too far from any star to generate meaningful power. Nuclear reactors might work, but they require fuel, coolant, and maintenance systems that must operate autonomously for centuries. Every power system we can imagine faces fundamental limitations that make millennial operation impossible. The manufacturing precision required for interstellar spacecraft exceeds anything humans have ever attempted. Every joint must remain sealed for centuries. Every moving part must continue functioning despite thermal cycling, radiation damage, and mechanical wear. Every electronic connection must maintain conductivity through temperature extremes and cosmic ray bombardment. Quality control becomes meaningless when testing timescales extend beyond human lifetimes. We can't test how materials behave after 500 years of space exposure because we haven't had access to space for 500 years. We must extrapolate from short-term tests, making assumptions about long-term behavior that may prove catastrophically wrong. The repair capabilities required for true long-duration missions approach science fiction. Spacecraft would need advanced robotic systems capable of manufacturing new components from raw materials, diagnosing complex system failures, and performing repairs in environments that would destroy any known technology. These repair systems would themselves need repair systems, creating infinite recursions of technological complexity. Even more fundamentally, interstellar spacecraft must be designed before they launch, using technologies available at the time of construction, but the journey takes centuries. By the time the spacecraft reaches its destination, human technology will have advanced beyond recognition. The spacecraft will be an antique, built with obsolete technologies, and designed to solve problems we no longer consider relevant. This technological obsolescence means that interstellar missions face a cruel paradox. They must be designed using current technology, but must operate using knowledge we don't yet possess. Every system must be perfect from the moment of launch, because there's no opportunity to apply lessons learned during the mission. The engineering requirements for interstellar travel don't just exceed our current capabilities, they exceed what may be physically possible. Building machines that operate flawlessly for millennia requires solving problems that may have no solutions, using materials that may not exist, with precision that may be unachievable. Each engineering challenge we examine reveals not just current limitations, but fundamental barriers that make interstellar travel an impossible dream. Among all the impossible challenges of interstellar travel, perhaps none is more psychologically devastating than the communication problem. The vast distances to Proxima Centauri b don't just make travel difficult, they create a communication black hole that would render any interstellar mission essentially autonomous from the moment it launches, transforming what should be humanity's greatest collective achievement into a lonely journey into cosmic silence. Light, traveling at the universe's ultimate speed limit, takes 4.24 years to cross the distance between Earth and Proxima Centauri. This means that even at the moment a spacecraft arrives at Proxima b, any message sent back to Earth won't arrive for another 4.24 years. Mission controllers receiving this message would be getting information about events that happened nearly a decade in the past, assuming the spacecraft somehow managed to travel at light speed. But realistic interstellar missions would travel much slower than light speed, making the communication delay catastrophically worse. A spacecraft traveling at 10% light speed would take 42 years to reach Proxima b. By the time it arrives and sends its first message, that message would take another 4.24 years to reach Earth. Mission controllers would be receiving their first arrival report 46 years after launch information about a mission controlled by people who are likely dead, using technology that has become obsolete, addressing questions that may no longer seem relevant. This communication black hole destroys the entire concept of mission control as we understand it. Every spacecraft humans have ever launched has maintained some form of communication with Earth. Mission controllers guide trajectories, troubleshoot problems, update software, and make real-time decisions based on spacecraft telemetry. This continuous connection between Earth and spacecraft has been fundamental to every successful space mission in history. For interstellar missions, this connection becomes meaningless. By the time mission controllers receive notification of a problem, the spacecraft has been dealing with that problem for over 4 years. Any advice or instructions sent back would take another 4.24 years to arrive, more than 8 years total response time for emergency situations. In spacecraft engineering, where system failures often require immediate response, 8-year communication delays make mission control impossible. The psychological impact on mission planners and the public would be profound. Imagine launching humanity's most ambitious and expensive mission, watching it disappear into the cosmic dark, then waiting nearly half a century just to learn whether it survived the journey. Generations of engineers, scientists, and taxpayers would live their entire careers, even their entire lives, without knowing whether their greatest efforts succeeded or failed. For crewed missions, the communication problem becomes existentially terrifying. Astronauts would gradually watch Earth fade from a world they could talk to into a distant memory they could barely contact. As the years pass, communication delays would grow longer, making conversations with family, friends, and colleagues impossible. Real-time interaction with Earth would cease within months of launch, never to resume. The psychological research on isolation and communication delay suggests that crews would experience profound mental health challenges long before reaching their destination. Antarctic researchers, submarine crews, and other isolated groups maintain their psychological stability, partly through regular contact with the outside world. Interstellar crews would face isolation more complete than any humans have ever experienced, with no possibility of meaningful contact with home. The cultural and linguistic evolution problem compounds the communication challenges. Human languages change significantly over periods of decades, let alone centuries. A crew launching today would reach Proxima b, speaking versions of English, Chinese, or Spanish that might be partially incomprehensible to the Earth populations they left behind. Scientific terminology, cultural references, and social contexts would have evolved beyond recognition. Even more problematic, the political and scientific priorities that justified the original mission would likely change completely during the journey. The organizations that launched the spacecraft might no longer exist. The governments that funded the mission might have fallen. The scientific questions the mission was designed to answer might seem quaint or irrelevant to future civilizations. The technology gap would make communication protocols obsolete. A spacecraft launched with today's communication technology would be trying to contact an Earth civilization using technology we can't imagine. It's like trying to communicate with modern internet infrastructure using telegraph equipment. The fundamental assumptions about data transmission, encoding, and protocols would be completely incompatible. Power limitations make long-term communication even more impossible. Radio transmissions across interstellar distances require enormous power to maintain signal strength. As spacecraft power systems degrade over decades or centuries of operation, the ability to transmit signals back to Earth would gradually disappear. The spacecraft might survive the journey but lack sufficient power to report its success. The communication black hole reveals why interstellar travel isn't just physically impossible, it's culturally and psychologically impossible. Humans have never attempted missions that lose contact with Earth for longer than a few hours. Interstellar missions would lose meaningful contact for decades or centuries, fundamentally changing what it means to be human explorers connected to human civilization. This communication isolation would transform interstellar missions from human endeavors into autonomous robot missions, even if they carried human crews. The psychological and cultural connections that make exploration meaningful would be severed by the vast distances and time delays that make interstellar travel impossible. The human challenges of interstellar travel extend far beyond radiation exposure and technological failures. Any realistic journey to Proxima Centauri b would require multiple generations of people to live and die aboard spacecraft, creating unprecedented social, psychological, and genetic problems that make manned interstellar missions impossible, even if we could solve every technical challenge. Generation ship spacecraft designed to support human populations for centuries or millennia present, the only conceivable approach to manned interstellar travel with foreseeable technology. These vessels would need to maintain closed ecological systems, providing air, water, food, and living space for potentially thousands of people across dozens of generations. The social engineering required for such missions may be more impossible than the technical engineering. The psychological research on long-term isolation and confinement reveals fundamental problems that would destroy interstellar missions long before reaching their destinations. Studies of Antarctic stations, nuclear submarines, and space station crews show that humans struggle with isolation and confinement even over periods of months. Psychological problems include depression, anxiety, interpersonal conflicts, and behavioral disorders that threaten mission success and crew safety. Interstellar missions would face isolation thousands of times more severe than any previous human experience. The crew would be completely cut off from Earth civilization, with no possibility of rescue, evacuation, or even meaningful communication. They would be trapped in a small artificial environment, breathing recycled air, drinking recycled water, eating recycled food, surrounded by the same people for their entire lives. The social dynamics of generation ships present unsolved problems that may have no solutions. How do you maintain mission focus across generations of people who never chose to participate in the journey? The original crew might be highly motivated volunteers, but their children would be prisoners born into circumstances they didn't select. By the third or fourth generation, most of the population would have no living connection to Earth or personal investment in reaching Proxima b. Cultural drift would inevitably destroy mission continuity. Human societies change rapidly, even under stable conditions. Language evolves, social norms shift, values transform. A generation ship population isolated for centuries would develop its own distinct culture, potentially losing connection to the original mission goals. They might decide that their spacecraft is their permanent home, choosing not to colonize Proxima b, even if they successfully reach it. The education and knowledge preservation problem compounds these social challenges. Interstellar missions require maintaining advanced technological knowledge across centuries of isolation. Crews must understand complex systems, perform sophisticated repairs, and operate scientific equipment throughout the journey. But knowledge degrades over generations unless actively maintained through education and practice. On Earth, we preserve technical knowledge through universities, libraries, internet resources, and professional communities. A generation ship would need to maintain equivalent educational institutions in a population of a few thousand people. Specialists would need successors, but with limited population and no contact with Earth's knowledge base, essential skills would inevitably be lost. The genetic diversity problem poses even more fundamental challenges. Any generation ship population must be large enough to avoid inbreeding depression over dozens of generations. Population geneticists estimate that maintaining genetic health requires at least 160 individuals, and preferably more than 500, to avoid serious genetic problems over multi-generational timescales. But larger populations require more massive spacecraft, which require exponentially more energy to accelerate to interstellar speeds. The genetic requirements for multi-generational survival directly conflict with the engineering requirements for interstellar travel. Every additional person aboard the generation ship makes the mission exponentially more impossible from an energy perspective. Even with adequate genetic diversity, the social dynamics of mate selection in closed populations create psychological pressures that Earth-based humans have never experienced. Everyone aboard the ship would know everyone else intimately. Privacy would be impossible. Social conflicts would persist for lifetimes, possibly destroying crew cooperation essential for mission survival. The authority and governance problem presents equally impossible challenges. Who makes decisions aboard a generation ship? The original mission planners will be dead within decades of launch. Democratic systems might evolve in directions that threaten mission success. Authoritarian systems might become oppressive, leading to rebellion or social breakdown. Any governance system must remain stable for centuries, while adapting to changing circumstances, a requirement that no human political system has ever achieved. Medical challenges compound all other problems. Generation ships must maintain complete medical capabilities, including surgery, obstetrics, dentistry, and treatment for every possible disease or injury. Medical knowledge and equipment must be preserved across generations, with no possibility of consultation with Earth-based medical expertise or importation of new treatments and technologies. The birth and death cycle creates profound psychological challenges unique to generation ships. People would be born into a closed world, live their entire lives in an artificial environment, and die without ever experiencing planets, weather, or the natural world their ancestors knew. The psychological impact of this extreme environmental deprivation on human mental health and social development remains completely unknown. Perhaps most crushing of all is the realization that generation ship populations would lose connection to the human experience that motivated interstellar travel in the first place. They would become isolated human subspecies, neither fully Earth-human nor adapted to their destination planet, trapped forever in artificial worlds of metal, and recycled air. Even if humanity somehow solved every impossible challenge we've discussed, the energy requirements, radiation exposure, engineering failures, and generational social problems, we would still face the most psychologically devastating possibility of all, arriving at Proxima Centauri b, only to discover that our destination is completely uninhabitable, making the entire impossible journey meaningless. Our knowledge of Proxima b remains frustratingly limited. We know it exists, we know its approximate size and orbit, and we suspect it might have temperatures suitable for liquid water. But beyond these basic facts, Proxima b remains a mystery wrapped in 4.24 light-years of distance and decades of technological limitations. The planet might have no atmosphere at all. Red dwarf stars like Proxima Centauri are notorious for producing stellar flares that can strip away planetary atmospheres over geological time. Computer models suggest that planets in Proxima b's position lose their atmospheres within millions of years of formation, leaving behind airless, irradiated wastelands, similar to Mercury but even more hostile. Even if Proxima b retained some atmosphere, it might be completely unsuitable for human life. The atmosphere could be too thin to breathe, like Mars. It could be too thick and toxic, like Venus. It could contain poisonous gases, extreme pressures, or chemical compositions that make surface exploration impossible. We have no way of determining atmospheric composition from Earth, so any interstellar mission would be traveling blind to an unknown destination. The surface conditions remain equally mysterious. Proxima b is tidally locked to its star, meaning one side experiences eternal daylight, while the other suffers permanent darkness. The temperature difference between these hemispheres could create violent weather systems that make the planet uninhabitable. The day side might be too hot for human survival, while the night side remains frozen solid. Liquid water, often cited as the reason for considering Proxima b habitable, might not exist at all. Even if temperatures allow liquid water, the planet needs the right atmospheric pressure and chemical conditions to maintain it on the surface. Water could exist only as ice or vapor, making the planet no more habitable than Mars, despite being in the theoretical habitable zone. The geological activity of Proxima b remains completely unknown. The planet could be volcanically active, with surface conditions that change rapidly due to tectonic activity. It could be geologically dead, with no magnetic field to protect against stellar radiation. It could have extreme topography that makes landing and colonization impossible. Even more problematic, Proxima b might harbor existing life forms that are incompatible with human biology. Alien microorganisms could be pathogenic to humans, creating biological hazards that make colonization impossible. Alternatively, human contamination might destroy indigenous life, raising ethical questions about interstellar exploration that we've never had to consider. The psychological impact of discovering an uninhabitable Proxima b would be devastating for any surviving crew. After centuries of travel, generations of sacrifice, and the expenditure of humanity's greatest resources, the discovery that their destination cannot support human life would represent the ultimate cosmic joke. The crew would face the choice of attempting an impossible return journey or establishing a doomed colony on a hostile world. But perhaps the most crushing realization would be that Earth-based humanity would never learn the results of their greatest gamble. Remember our communication delays. By the time a crew reaches Proxima b and determines its habitability, their assessment wouldn't reach Earth for another 4.24 years. The civilization that launched the mission might no longer exist. The scientific questions that motivated interstellar travel might seem irrelevant to whatever human society persists on Earth. This uncertainty reveals why interstellar travel represents not just a technological impossibility, but a fundamental gamble, with odds so poor that no rational civilization would attempt it. We would be betting everything on a destination we can barely observe, using technology that doesn't exist, over timescales that exceed human historical experience. The arrival problem transforms interstellar travel from an engineering challenge into a cosmic lottery with stakes so high and odds so poor that purchasing a ticket would represent civilization-level insanity. Even if we could solve every other impossible barrier to reaching Proxima b, we might be solving them only to reach a world that makes our entire effort meaningless. In 2016, as excitement about Proxima b's discovery reached fever pitch, Silicon Valley billionaire Yuri Milner announced the breakthrough Starshot initiative, a $100 million project to send tiny spacecraft to Proxima Centauri using laser propulsion. The proposal captured global imagination, promising to solve interstellar travel through revolutionary technology and entrepreneurial innovation. But like all proposed solutions to the Proxima b problem, breakthrough Starshot falls apart under rigorous scientific scrutiny, revealing why even our most optimistic breakthrough proposals can't overcome fundamental physics. The breakthrough Starshot concept sounds elegantly simple. Build thousands of tiny spacecraft, each weighing just a few grams, and equipped with gossamer light sails. Focus enormous ground-based lasers on these sails, accelerating the spacecraft to 15–20% of light speed within minutes. At these velocities, the tiny probes would reach Proxima Centauri in just 20–25 years, finally making interstellar exploration feasible within human lifetimes. The project attracted support from Stephen Hawking, Mark Zuckerberg, and other luminaries who lent their credibility to what seemed like humanity's first realistic interstellar mission. Popular media breathlessly reported that we might receive the first photographs of another star system within decades. The dream of interstellar travel seemed tantalizingly close to reality. But the fundamental physics problems with breakthrough Starshot are insurmountable, beginning with the laser power requirements. To accelerate even a gram-scale spacecraft to 15% of light speed requires approximately 10–15 watts of laser power applied for several minutes. For comparison, the entire electrical generating capacity of human civilization is about 3×10⁻12 watts. Breakthrough Starshot would require laser power equivalent to roughly 300 times total human electricity production, focused with perfect precision on targets the size of postage stamps. The engineering challenges of building such laser systems exceed anything humans have ever attempted. The lasers would need to maintain perfect coherence across distances of hundreds of kilometers, focusing gigawatts of power onto sails just centimeters across. Atmospheric turbulence, thermal effects, and mechanical vibrations would scatter the laser beams, making precise targeting impossible. Even minor focusing errors would vaporize the delicate spacecraft rather than accelerating them. But assume we could somehow build these impossible laser systems. The spacecraft themselves present equally insurmountable challenges. At 15% of light speed, even individual atoms in interstellar space become high-energy projectiles that would destroy any known material. A single collision with an interstellar dust grain would vaporize the entire spacecraft, creating a spectacular but brief fireworks display in the cosmic void. The communication problem makes breakthrough Starshot particularly absurd. The proposed spacecraft would weigh just a few grams, including all scientific instruments, communication equipment, and power systems. Radio transmitters capable of sending signals across 4.24 light-years require significant power and antenna size requirements that dramatically exceed what gram-scale spacecraft could possibly carry. Even if the tiny spacecraft could somehow transmit signals back to Earth, the power requirements for detection would be astronomical. Radio signals follow inverse square laws, meaning signal strength decreases with the square of distance. Signals from Proxima Centauri would arrive at Earth with power levels measured in attawatts-so-weak. They would be completely overwhelmed by background radio noise from terrestrial and cosmic sources. The data transmission rates would be pathetically slow, even under the most optimistic assumptions. Transmitting a single high-resolution image would require years of continuous transmission at maximum power that gram-scale spacecraft couldn't generate or store. The scientific return from breakthrough Starshot missions would be virtually zero, even if everything else worked perfectly. Manufacturing thousands of identical gram-scale spacecraft presents production challenges that dwarf anything in human industrial history. Each spacecraft would need to be assembled with precision exceeding that of the finest Swiss watches, while incorporating advanced electronics, propulsion systems, scientific instruments, and communication equipment. The quality control requirements alone would make production impossible at any reasonable cost. Perhaps most damaging to the breakthrough Starshot concept is the fundamental lack of guidance systems. Once accelerated by lasers, the tiny spacecraft would coast through interstellar space for decades with no ability to adjust course, navigate around obstacles, or respond to unexpected conditions. They would be ballistic projectiles, not spacecraft, with essentially zero probability of actually encountering their intended targets. The trajectory precision required for interstellar missions exceeds human engineering capabilities by orders of magnitude. Launch errors of microradians would result in spacecraft missing entire star systems by millions of kilometers. There's no way to correct course during flight, no way to adjust for gravitational perturbations or measurement errors. The spacecraft would disappear into interstellar space and never be heard from again. Breakthrough Starshot represents the most optimistic thinking about interstellar travel, backed by serious money and distinguished scientists. If even this revolutionary proposal fails under scientific scrutiny, it reveals how fundamental the barriers to interstellar travel really are. The problems aren't just engineering challenges waiting for better technology. They're physics barriers that no amount of innovation or investment can overcome. The failure of Breakthrough Starshot doesn't just doom one particular approach to interstellar travel. It demonstrates why all proposed solutions to the Proxima b problem ultimately fail when confronted with the uncompromising mathematics of physics and engineering. When conventional rockets and even revolutionary laser propulsion fail to solve the interstellar travel problem, many scientists and futurists turn to fusion rockets as the ultimate solution. Fusion represents the most powerful energy source humans can realistically hope to harness, the same process that powers stars themselves. If fusion rockets can't make interstellar travel feasible, the reasoning goes, then nothing can. But even perfect fusion technology, operating with magical efficiency that exceeds anything possible in the real world, still falls catastrophically short of making journeys to Proxima Centauri b practical or possible. Fusion rockets promise extraordinary performance compared to chemical propulsion. Where chemical rockets achieve exhaust velocities of perhaps 4-5 kilometers per second, fusion rockets could theoretically reach exhaust velocities of 3.010 kilometers per second, roughly 3/10% of light speed. This dramatic improvement seems to solve the fundamental problem of interstellar travel. If your exhaust is moving fast enough, you can accelerate spacecraft to significant fractions of light speed without requiring impossible amounts of fuel. The fusion advantage becomes apparent when we revisit our earlier rocket equation calculations. Using fusion exhaust velocities of 6.0 kilometers per second, 2% of light speed, accelerating a spacecraft to 10% of light speed would require a fuel-to-payload mass ratio of about 150. This seems almost reasonable compared to the impossible ratios required by chemical rockets. A 10-ton spacecraft would need 150 tons of fusion fuel massive, but at least within the realm of conceivable engineering. This apparent feasibility has led to decades of serious scientific studies of fusion-powered interstellar missions. Project Daedalus, conducted by the British Interplanetary Society in the 1970s, designed a fusion spacecraft that could reach nearby stars in 5,100 years. More recent studies have proposed even more advanced fusion systems, some claiming the ability to accelerate spacecraft to 15–20% of light speed, making interstellar travel feasible within human lifetimes. But these optimistic projections rest on assumptions about fusion technology that remain fantasy more than 70 years after the first hydrogen bomb demonstration. Controlled fusion for power generation has been just 20 years away for the past 5 decades, despite billions of dollars in research and the construction of increasingly elaborate experimental facilities. Every breakthrough in fusion research reveals new technical challenges that push practical fusion power further into the future. For rocket propulsion, the fusion requirements become exponentially more difficult than stationary power generation. Fusion reactors on Earth operate in carefully controlled laboratory environments with massive magnetic confinement systems, superconducting magnets cooled to near absolute zero, and armies of technicians monitoring every parameter. A fusion rocket must achieve the same controlled nuclear reactions while being shaken by enormous accelerations, exposed to cosmic radiation, and operating autonomously for decades without maintenance. The engineering challenges of space-based fusion exceed anything we can currently imagine. The magnetic confinement systems required for fusion reactions must operate in the vacuum and temperature extremes of space while maintaining perfect plasma containment. Any loss of magnetic confinement would instantly destroy the spacecraft in a miniature stellar explosion. The power systems, cooling systems, and control systems must all function flawlessly for the entire multi-decade journey to Proxima Centauri. But even if we assume perfect fusion technology, 100% efficient energy conversion, magical plasma confinement, and flawless reliability, the fundamental physics of interstellar travel still make Proxima B missions impossible. The energy requirements we calculated earlier remain unchanged. Perfect fusion simply means we can convert matter to energy with maximum theoretical efficiency, but we still need impossible amounts of matter to provide the required energy. Remember that our modest 0 kilogram spacecraft mission to Proxima Centauri at 10% light speed requires approximately 4.5 Chepels 17 joules of kinetic energy. Even with perfect fusion efficiency, this translates to about 5 kilograms of matter converted completely to energy, according to E². But fusion doesn't convert matter to energy with 100% efficiency. Even hydrogen fusion converts less than 1% of matter to energy. Realistic fusion reactions would require roughly 500 kilograms of hydrogen fuel just for the kinetic energy needed to accelerate our small spacecraft. Add the fuel needed for deceleration, life support, course corrections, and spacecraft systems, and we're back to fuel requirements that dwarf the spacecraft payload. The rocket equation hasn't been defeated, it's simply been delayed by one level of technological optimism. The fusion, fuel storage, and handling problems compound these impossibilities. Hydrogen, the lightest possible fusion fuel, must be stored as liquid at temperatures near absolute zero, or as compressed gas under enormous pressures. Either storage method requires massive, heavy containment systems that add to spacecraft mass. Helium-3, often proposed as an ideal fusion fuel, exists in negligible quantities on Earth and would require mining operations on the Moon or outer planets themselves, requiring massive infrastructure investments that make interstellar missions even more impractical. The fusion reactor mass represents another crushing problem. Current experimental fusion reactors weigh thousands of tons and require massive supporting infrastructure. Even optimistic projections suggest that practical fusion reactors suitable for spacecraft might weigh hundreds of tons, again driving up spacecraft mass and fuel requirements exponentially. The power-to-thrust ratios achievable with realistic fusion systems fall far short of interstellar mission requirements. Fusion reactions produce enormous amounts of energy, but converting that energy to directed thrust requires additional systems, magnetic nozzles, power conversion equipment, and cooling systems that reduce overall efficiency and add mass. The net result is propulsion systems that, while impressive compared to chemical rockets, still can't achieve the sustained high accelerations needed for practical interstellar travel. Perhaps most damaging to fusion optimism is the realization that we're still decades away from achieving controlled fusion under laboratory conditions, let alone developing space-rated fusion rockets capable of multi-decade autonomous operation. The gap between our current fusion capabilities and interstellar mission requirements is so vast that fusion represents hope rather than realistic technology. The fusion fantasy reveals how even our most optimistic breakthrough technologies fail to overcome the fundamental barriers to interstellar travel. Perfect fusion would represent humanity's mastery of stellar-level energy sources, but even stellar-level technology isn't sufficient to make journeys to Proxima Centauri B feasible. The universe has constructed barriers so fundamental that they exceed the capabilities of star-powered civilizations. In 1950, physicist Enrico Fermi posed a question that has haunted scientists for over 7 decades. Where is everybody? If the universe contains billions of potentially habitable planets, and if intelligent life should be relatively common, why haven't we detected any evidence of other technological civilizations? The apparent absence of alien visitors, radio signals, or megastructures throughout our galaxy has become known as the Fermi paradox. Our analysis of the Proxima Centauri B problem suggests a disturbing but elegant solution to Fermi's question. Perhaps we haven't encountered other civilizations because interstellar travel is fundamentally impossible for any technology-based species, regardless of their advancement level or determination. The barriers we've examined: energy requirements that exceed planetary resources, radiation that kills biological life, communication delays that destroy mission coherence, and engineering challenges that exceed material capabilities, may be universal constraints that trap every civilization within their home star system. This isn't a failure of human engineering or imagination. It's the universe operating exactly as the laws of physics dictate it must. Einstein's speed limit isn't just inconvenient for human space travel, it's a fundamental barrier that prevents all matter-based civilizations from spreading across the galaxy. The rocket equation doesn't discriminate based on species intelligence or technological sophistication. Cosmic radiation doesn't become less lethal for aliens who might have evolved different biology. The mathematics we've explored are universal. Any civilization attempting interstellar travel would face identical energy barriers, identical radiation environments, identical communication delays, and identical engineering impossibilities. The most advanced alien civilizations, with technology millions of years beyond ours, would still be trapped by the same physical laws that make our own interstellar ambitions impossible. This realization transforms our understanding of galactic civilization. Instead of imagining a galaxy teeming with interstellar empires, spacefaring species, and galactic federations, we might live in a universe where every intelligent civilization remains forever bound to their birth star system. Each civilization would be an isolated island of consciousness, aware that others likely exist but unable to ever make contact across the vast gulfs of interstellar space. The implications are both humbling and profound. Humanity's failure to achieve interstellar travel wouldn't represent some unique limitation of our species. It would place us among all the other intelligent civilizations in the galaxy, each struggling against the same impossible physics, each ultimately defeated by the same universal barriers. We would be part of a community of isolated civilizations, connected by our shared inability to connect with each other. This cosmic quarantine might explain not just the absence of alien visitors, but the absence of any detectable evidence of galactic-scale engineering projects. If civilizations can't spread between star systems, they can't build galaxy-spanning megastructures, harvest energy from multiple stars, or engage in the large-scale cosmic engineering that some scientists have proposed as signatures of advanced civilizations. The Fermi solution suggests that SETI's search for extraterrestrial intelligence might be fundamentally flawed in its assumptions. We're not searching for evidence of galactic civilizations because galactic civilizations can't exist. We're searching for radio signals from interstellar spacecraft that can't be built. We're looking for evidence of cosmic engineering projects that physics makes impossible. Instead, alien civilizations would be doing exactly what we're doing, developing technology within their solar systems, perhaps sending robotic probes to nearby planets, certainly wondering about the existence of other intelligent life, but forever unable to make contact across interstellar distances. They would face the same crushing realization we're confronting, that consciousness appears to be quarantined by the fundamental structure of space-time itself. This doesn't mean that technological civilizations are rare or unsuccessful. It simply means they're all prisoners of physics, just as we are. The galaxy might contain thousands or millions of intelligent species, each developing their own unique cultures, technologies, and understanding of the universe, but each destined to remain forever isolated in their cosmic island homes. The Fermi solution transforms our cosmic loneliness from evidence of failure into evidence of universality. We're not alone in being alone, we're part of a galaxy-wide community of isolated civilizations, each facing the same impossible barriers, each trapped by the same unforgiving mathematics of interstellar travel. After examining every barrier to interstellar travel, the crushing energy requirements, lethal radiation environments, impossible engineering challenges, and fundamental physics limitations, we arrive at a conclusion that's both sobering and liberating. Earth will always be humanity's only home, and this may be exactly as it should be. The dream of reaching Proxima Centauri b has captivated our imagination precisely because it seems so tantalizingly close. At just 4.24 light-years away, it appears to be within reach of sufficiently advanced technology and determination. But our analysis reveals that close in cosmic terms still means impossibly far in human terms. The nearest potentially habitable world might as well be in another universe for all the possibility we have of reaching it. This realization forces us to confront a fundamental truth about human civilization. We are a terrestrial species, evolved over millions of years to thrive in Earth's specific environment. Our biology, psychology, and social structures are all adapted to this one planet's gravity, atmosphere, temperature range, and day-night cycle. We are not cosmic explorers by nature. We are Earthlings who have developed tools that allow us to briefly leave our home, but never to permanently abandon it. The impossibility of interstellar travel doesn't represent a failure of human ingenuity or ambition. It reveals something profound about the structure of the universe itself. The cosmos appears to be organized in a way that allows complex life to evolve on countless worlds, while preventing that life from spreading between star systems. This cosmic quarantine may be a fundamental feature of how the universe manages complexity and intelligence. Consider the alternative. If interstellar travel were easy, the galaxy would likely have been colonized billions of years ago by the first species to develop advanced technology. The fact that Earth hasn't been overrun by alien civilizations suggests that we're all trapped by the same physical barriers, all limited to our individual star systems, all forced to make the best of our cosmic circumstances. This constraint may actually be beneficial for the development of intelligence and consciousness. Isolated civilizations must solve their own problems, develop their own unique perspectives on existence, and create their own meaning within their limited cosmic domains. If interstellar travel were possible, dominant civilizations might have homogenized the galaxy, preventing the diverse flowering of consciousness that isolation enables. The impossibility of reaching Proxima Centauri b redirects human ambition toward more achievable and ultimately more meaningful goals. Instead of fantasizing about distant worlds we can never reach, we might focus on fully exploring and understanding the solar system that is actually accessible to us. Mars, Europa, Enceladus, and Titan all offer genuine possibilities for human exploration and perhaps even settlement within the next century. More importantly, Earth itself remains largely unexplored and poorly understood. We've mapped less than 20% of the ocean floor. We don't fully understand our planet's climate systems, biological diversity, or geological processes. The deep biosphere, the upper atmosphere, and the polar regions still hold countless mysteries. Before dreaming of other worlds, we might first master the one that gave us life. The energy and resources that would be required for impossible interstellar missions could instead be directed towards solving humanity's existential challenges on Earth. Climate change, biodiversity loss, social inequality, and the sustainable management of planetary resources all require massive investments in technology and international cooperation. These are problems we can actually solve, unlike the impossible physics of interstellar travel. Our cosmic isolation also has profound philosophical implications. If humanity represents the universe's attempt to understand itself through conscious observation, then our role is not to spread across the galaxy, but to develop the deepest possible understanding of cosmic reality from our unique vantage point. We are the universe's eyes and mind in this particular location, evolved specifically to comprehend and appreciate the cosmos from Earth's perspective. The barriers to interstellar travel may preserve something precious about human consciousness, our connection to the planet that shaped us. If we could easily abandon Earth for other worlds, we might lose the humility and environmental awareness that come from being permanently bound to a finite, fragile biosphere. Our cosmic prison might actually be our cosmic sanctuary, protecting us from the hubris that unlimited expansion might bring. This doesn't mean we should abandon space exploration entirely. The solar system offers vast opportunities for scientific discovery, resource utilization, and perhaps even human settlement. We can and should continue pushing the boundaries of what's possible within the cosmic domain that's actually accessible to us. But we should do so with the understanding that Earth will always remain our primary home, our evolutionary origin, and our ultimate responsibility. The impossibility of reaching Proxima Centauri b doesn't diminish human potential, it clarifies it. We are not destined to be galactic conquistadors, but rather the conscious caretakers of one precious world among countless others scattered throughout an vast, beautiful, and forever inaccessible universe. In accepting our limitations, we find our true purpose, not to escape Earth, but to understand it, protect it, and help it flourish as the irreplaceable home of human consciousness in an cosmos that will always hold us, lovingly and firmly, in its gravitational embrace. And so we return to where we began. Proxima Centauri b still orbits its red dwarf star, just 4.24 light-years away. It still represents the closest potentially habitable world to Earth. The distance hasn't changed. Our desire to reach it hasn't diminished. But everything else has changed. We now understand that this cosmic neighbor exists behind barriers more impenetrable than any wall humans have ever encountered. The universe has constructed the perfect prison around every star system. Energy requirements that exceed planetary resources, radiation environments that destroy biological life, communication delays that sever human connections, engineering challenges that surpass physical possibility. These aren't temporary obstacles waiting for better technology. They are fundamental features of reality itself. Einstein's equations don't care about human ambition. The laws of thermodynamics aren't impressed by technological optimism. Physics doesn't negotiate. Perhaps this is exactly as it should be. In a universe where interstellar travel were easy, consciousness might never have evolved the depth and diversity we see around us. Every world would be colonized by the first successful species. Every civilization would be an echo of whoever arrived first. The cosmic quarantine that frustrates our interstellar dreams may be the very mechanism that allows intelligence to flourish in countless unique forms across countless isolated worlds. We are not alone in being alone. Somewhere in the cosmos, other civilizations are making the same discoveries we've made today. They're calculating the same impossible energy requirements. They're confronting the same lethal radiation barriers. They're accepting the same cosmic constraints that define the boundaries of possible ambition. Humanity's destiny isn't written in distant stars. It's written in the one star system we can actually reach. Our future lies not in abandoning Earth, but in finally understanding it. Not in escaping our cosmic prison, but in recognizing it as our cosmic sanctuary. The universe is vast, beautiful, and forever beyond our reach. And in that impossibility, we find not limitation, but the precise scope of human purpose. To be the conscious observers of one precious world, understanding our place in a cosmos that will always be larger than our ability to explore it. What strikes you most about our cosmic limitations? Do you find them frustrating or oddly comforting? Share your thoughts in the comments below. If today's journey through the impossible physics of interstellar travel has left you both humbled and fascinated, I'd be honored if you'd hit that like button and consider subscribing. Each video on this channel explores the profound realities that shape our universe, and your support helps ensure we can continue asking the big questions together. The cosmos holds countless more mysteries worth exploring, each revealing new depths to the universe we call home. Ready to continue your cosmic education? Our playlist awaits with more revelations about the beautiful, impossible, and endlessly surprising reality we inhabit. The next discovery is just a click away.